But if I record, it's going back here. So let me go here. Okay. Okay, so polymer means many part, or some people prefers the macromolecule, which means it's a molecule, but it's quite large compared with other chemical entities. And back then, although people already know about rubber, like natural rubber, but they don't really know what is polymer means or what is macromolecule means, because they have different perspective on what the rubber is in terms of chemical inside. Okay? So the concept of this giant molecule, I think I also said before, is like comparing the colloids. Okay? So if we see the colloids, we know that the colloids has enough viscosity that they have some certain of, when we deal with, we try to vaporize, or maybe we want to diffuse them in some solutions. If it is some crystalloid, because of the structure, very small structure that made up and becomes big, if we diffuse them, it diffuses easily because of small structure. But for colloids, because it has large molecule, it's not easy. So when we diffuse them, it seems like they're acting like a glue, like they have some viscosity. Okay, now scientists approach that, perhaps we need to look on different perspectives. So the assumptions that the chemical approach, they assume that the colloid substance were in fact large molecules, and the behavior can be explained with the size. Okay, so the size of the individual atoms, okay, or individual molecules. Okay. But the physical approach, so we have chemical and we have a physical approach. Okay. But for physical, it doesn't really matter. Large, small, it doesn't really matter. The important thing is, or let me write here, favorite concept of molecular size were no different in magnitude from the crystalloid materials, but the colloidal behavior is, or was, it's a consequence. Okay? It's a consequence of the aggregations of the smaller molecules in solutions that were held together by physical forces. That is from physical perspective. So there are two different perspectives that time. It's a long time ago, probably around 50 or 60. I think this probably around 50s. But when we deal with the testing, the experiment, the physical approach were success. Okay, they successfully convinced people. So the physical approach, they prevailed because for that time it is true. It is suitable for the methodology that time. Okay. But then, if you want to look in more organic chemistry, then we need to have another preparation. So we need to make sure that we understand this part. Okay. So the organic chemistry demand preparation and investigation of the pure substance. Okay, and they need to also consider the melting points, the molar mass. Okay, and when the experiment it's fit with the physical approach, the problem is then comes from the rubber latex. Okay, so when people decide, so they are actually trying to find how the molecules inside the colloids that they still call colloids, what kind of structure that they will have. So people will still consider, oh, is it going to be like really long chain? But people that time didn't think about that. Okay? They don't really think that the chemicals can be formed like the small part can be like a puzzle, like you can make really, really long. So they don't think like that. Even though that is the truth is that, right? The true structure. So when we deal with this rubber, the first one is actually the actual structure that they will have, right? But people that time still think that the second one is best choices. Okay? So majority believe here, majority believe that only small molecules could exist as chemical entities. So that the possibility for the structure one forming long chains, it's not really considered. Okay? So they don't consider the first one going to be chained with really long chains. Okay? Oh yeah, it's 1927 was really, really long time ago. So, and then from the around 30s or 1927, so people were convinced that, in fact, the colloid substance is actually long, linear, thread-like molecules. And they are composed of small, we call the molecular units, it's definable. So we know that they will form sort of linear long chains, but we know the part inside, the small part, is really has some defined structure. Okay? Like polyethylene, which means it has an ethylene inside that is going to be repeat itself. Right? And of course, covalently bonded for each carbon atoms. Okay? And then it's forming the macromolecules. All right. Okay. Now, a little bit of history, but I will just maybe really fast, just skipping through, just to see that how people introduced polymer, what kind of product they made before. So, of course, the first civilizations that we know using polymers, probably Aztec, but I believe maybe before Aztec they already know and they already used in natural rubber, and probably they make some product that is elastic product, for example, and then we jump to 1828. This is I think the very first time, if I'm not mistaken, they synthesized urea from inorganic compounds. But they still don't understand what it is, how to make out from this urea. Okay. But then, 1850s, around 20 years later, some scientists they write the proper structure formula, and then Goodyear, Charles Goodyear, we know that it's now tire, right? A tire, right? At the first time, experiment on like a gum, the natural gum, malodorous gum, and he discovered vulcanizations. This is a process. It's like a cross-link process, but I think we will learn that maybe when we touch upon the elastomer. It's kind of rubber, and to make the cross-link. Okay, so he transformed the natural rubber and then forming the softenable thermoplastic. Okay. Yeah, this cross-link chain. Yeah, through creation of cross-link chain. Okay. For FYI, I will just mention here. I'll mention later again with more details. That we have two kinds of polymers. So we can define polymers by some classification, but one classification that we can define is thermoplastics and thermosets. Okay, thermoplastics is basically you can say it's two-dimensional molecules. Basically, it's like maybe a linear, you can say a linear chain. They can be softened by heating. Right? So usually in industry, we will see that mostly the thermoplastic, they will have some mold, they will have some injections, and they will have some process, like they give some energy. If they give energy, for example, usually they will have like we say like a pellet. So we put into the intruder, and then it goes up, and then it will heat up and becomes, we say, softened. And through some, maybe they will have some molding, and then some injection, and then we can maybe create some shape. Okay? So it starts from the pellets. It starts from like a pellet like this, and then probably goes here, some process here, and maybe along the way, it will be, the temperature will be going to be increased. Okay, and then or maybe let me use yellow for the polymer to see, and then it will goes here, it will heaten, and then it will be melted. We call this is the softened one. So we say it's melted. Okay, it's melted, and then we can put into some molds. Maybe this is the molds. Let's say this is the molds. Like maybe the easiest one, making the toys, like a plastic toys, and then it goes here. Maybe this is the molds. The molds are like that, and then it goes inside. Okay, so this is the mold. Okay, it's the middle part is probably inside. Maybe if it is like a big industry, maybe like a conveyor belt to transport the polymer. But anyway, that's thermoplastics. But the difference between the thermoplastic and thermoset is, for thermoplastic we can reshape as many as we want. So from pellets become product. If you want to heat up, it becomes soft. We can create another shape, and we can create as many as we want. That's thermoplastic. But for thermoset, it created usually by cross-link chain, like resin. If you know resin, yes. Yeah, resin, right? So resin, when they finish the curing, if you want to make it make it like reshape again, we cannot do that. Also, if you see the tire in car, it's also thermoset. We cannot really do anything. If we try to burn, it will like having a smoke, right? We cannot do anything. Okay, so rather than melting, thermoset will be degraded. So it's not really a melting; it's degraded. And then another thing is, scientists also found that the sulfur, if it's increased, the rubber will become having a little bit harder property. Okay. And then the rubber itself, at the beginning, it's really not really good looking materials. It has generally dull and dark in colors. So people try to find a way to make the colors maybe more beautiful. And Alexander Parks, he found the Parkinson, and from there he made the material can be brightly colored, okay, or clear even, or maybe making the material becomes shiny. And then the rubber will develop more and more. If, of course, here is by Dunlop, also well-known tire. And the automobile was emerging, trending. People going to invest a lot of money in automobile at that time. And bakelite found. This is also from synthesizing polymeric materials, and it's used for gears, cookware, phonograph record that time. Bowling balls also from bakelite. While it's still not recognized as a polymer at that time, the bakelite or bakelite, but he appeared to have some understanding on how to use the functionality on the bakelite, and then producing the thermoplastic materials and convert it to thermosets. So how to convert is basically in technical to initiate a crosslink, okay? To initiate a crosslink, and before they know the polymers, they are already doing that. Okay? And then PVC, polyphenol chloride, founded initially formed by Bowman, but not really getting interesting until 1926. This is when adhesive is becoming more and more huge, adhesive and sheaths. Okay, and then polystyrene. Okay, also it's found actually 1839. It's quite long, but how people use the polystyrene is 100 years later, because so it's really late, because maybe they don't really understand that time how to use it. Okay, and then they selling polystyrene commercially, and then plexiglass. Okay, plexiglass also a polymer. It's like a glass but a plastic. Maybe if you see how to say canopy, it's sometimes plexiglass. Some gear for shield, some of them are plexiglass, but most of the time nowadays it's a polyurethane, because it's more good for holding an impact. So this is I think replacement for glass that time. And then the colloids was introduced for some interval dimension. So people will say, oh, it's colloid, if they know the dimensions is between the nano and until micron, but not really micron, but maybe before micron, okay, up until micron. And polymer, they also within this range. So that's why people confused before. They cannot really differentiate the macromolecule and the original colloids. Colloid force is ionic, okay, or secondary force. And remember, if we talk about polymer, we talk about covalent bond, okay, the difference. So the important thing here is also polymers, they cannot be reduced without breaking the covalent bonds. Okay. 1860 oligomer prepared from ethylene glycol. This is also quite popular polymer, especially for chemical experimentations, because it's easily to be adjusted. It's simple structure, ethylene, and just adding glycol, the alcohol. And people use for its functionality. Its alcohol is really useful. And they also find how to write the structure correctly. Okay, they try to make the structure correctly, but still it's not considered as a polymer. Okay. And then 1880, some phytic made polymetallic acid, but it was incorrectly assigned some cyclic structure inside. So because they are still not really aware of what's happening. Okay. So people still thought on colloids, okay, or any cyclic compounds like cyclohexane. And still, within this period of time, the idea still not accepted the large molecules. And then the Staudinger, some refers this person as a father of polymers. He studied, especially isoprene, studied the difference between synthetic and natural rubber. And then he was told by his colleague when he wanted to discover more and more about these differences. And this is, I think, really, really interesting. He said, the study, the dear colleague, leave the concept of large molecules alone. There can be no such thing as a. So people really polarizing between, like a few people try to find the real structure, but other they just accept that we already have what we have. So we don't really think the macromolecule exists. So this is really interesting. But then Staudinger still experimenting, and then proposing linear structure for polyoxymethylene and polystyrene. And at the same time, X-ray also confirmed that the structure existed. Okay, the structure existed. Okay, structure proof. Okay, and also after Staudinger comes characters. He joined. This is also important. We also say that this is a father of synthetic polymer science. The first thing, that really important step in his life is joining this group, okay, and then developing some process for synthetic rubber. Okay. By joining the DuPont group, what does it mean? It has money, so he can do more experiments. I think it's also important. And then later, they sold the rubber. It's called the neoprene or duprene. And other scientists also joined characters, and they began another big steps here. It's polyamide fiber, and then successively formed fiber 66, or we call nylon 66, or 6,6. The 6 means it's representing the 6 carbon of atoms, and it's formed this fiber 66, and we rename this as nylons. Okay. And then from this nylon, it's really changed how the polymers works. Okay, how they can process, how can they synthesize, and it's become trend in 1930s. Okay, and then from the study, from the characters. He found out that polymers, it can be formed by employing organic reactions, but with reactants that had more than one reactive group per molecule. So he tried to find the reactive group through possibility is the functional groups. Okay? The functional groups, they can open some way, and then they make some link between these two. Okay, and then the force that bring together the individual polymer units are the same as those that held together. So it means that the bonds is the same. So the primary bonds. So that's why polymers is linked quite strong, okay, compared with the colloids. Okay, And during this time, during these characters, the names, ideas, they will all standardize. How to write the name, including the trade names also. So standardized. And also, the war happening, World War II, Kevlar and Teflon is developed. Of course, the Kevlar is for ballistics, right? For ballistics. And yeah, in one way, although war is bad, but in another perspective, it's helped us to grow and help us to develop this. Okay. So this is another point of view. So after this 1930s, scientists agree that polymer is or were chain-like molecules. Okay. And the viscosities of these macromolecules will be depend on the size and shape of the molecules in solutions. Okay. And if we see the classes, one way to see is also we can divide the polymers between the natural and synthetic. That's also one classification. Okay. And after 1940s, the polymer technology really grow. Okay. If you take, have you taken material science?
Yeah, I'm taking material.
Right now, right? Yeah. If you classify metals, ceramics, polymers, that are three basic materials, right? Well, there is four, the composite, but composite is combination of these three. But if we think on these three metals, ceramics, and polymers, the one that are really grow, if we see over a period of time, is a polymer. Metals, somehow it's like, because people already cultivate most of metals, so not really anything new. Ceramics probably still also develop, but ceramics, they also combine with polymers, they create something new. And most ceramics, I think now people using it for electronics, like for the semiconductors. But they usually use some concept from polymers, like the polymerizations. Okay, that's we can also see, and we see also the production. Okay, the production of some thermoset and thermoplastic. This is just an U.S. productions. This is millions of pounds. Pounds is half of kilogram, right?
I 30.6.7.
Yeah. 0.7 probably, right? Or half? Yeah, around half to 0.7. I forgot. Yeah, but yeah, this is interesting. And of course, if we see the numbers, this polyethylene and polypropylene is really high amount because they are all in packaging, in bottle, and people use that. But it create another negativity because of the pollutions and the pollution. So the polymers technology also now consider sustainability, or we call the green materials, Okay, next part is just a small summary, and then we can move to other slides. But I think the other slides I will just take some moments. Okay. So this is my summary here, okay, for the first slides. So polymers, first is definitions. Okay, so definitions in my words is giant molecules with molecular weights at least 100 times greater than those of smaller molecules such as water or methanol. Okay. And almost everything else is actually a polymer if we maybe disregard inorganic or metals. And most polymer, or all polymer, they have similar structure and governed by the same theories. Okay. Linear polymers consist of long chains with covalently bonded carbon atoms. Most linear polymers are thermoplastics. So we can say this is thermoplastic. They can be softened by heat and hardened by cooling in a reversible process. But linear polymers such as cellulose, they will have strong intermolecular forces like hydrogen bond. They cannot be softened by heating below the combustion temperature. This is just some I think, some restrictions that not all polymers behave the same, but most of the time for thermoplastic they will have uh, that property. Okay, and then we have the thermoset polymers that are cross-linked, and they cannot be softened by heating. Okay? And thermoplastic can be transformed to thermoset by some cross-linking. So we call the cross-linking agents, okay, to initiate some or to opening the site. Okay, to opening the site. The bakelite resins, they can be transformed to thermoset by introducing the cross-links between polymer chains. Okay. Early development in polymer technology were empirical because lack of polymer science knowledge. This is, I believe, in the first part of the lecture. And advancements is really rapid in 1930s, 1940s. Thermoplastic resolved resins that may be thermoset by heating are obtained by heating phenol and formaldehyde on the alkaline side. This is just a technical terms, how to make the thermoset. Okay. Yeah, I think that is the part. The second part, I believe, not really until the end of the presentations, but I think I will just goes through some definitions. Okay, we can also define polymer. Okay, I write different words, but I hope you can take the principles. So it's large molecules, it's covalently bond. Okay, you can say it's also have some. You can say about the unit of size or shape. So okay, or you can say many units or many repeated units also okay, repeated units. So you can say repeated units. It's also okay. Okay, the requirement, the essential things is for the small molecule to be qualified as a monomer is they need to be required to have the bonding sites. Okay? So 2 or more bonding sites. That's one requirement, which they can link up with other monomers, okay, to form the polymer chain. And the number of the bonding sites is what we refer to the functionality. Okay, like for example. I think in the first part I mentioned about the alcohol. Okay. So alcohol, if we can divide the oxygen and hydrogen and makes empty space for any bonding sites, that becomes functional. Okay. Okay, that's the I think the essentials part. So functionality. We can say that monomers such as the hydroxy acids or phenyl chloride, they has two functions. They are called bifunctional. Okay. The reactions, you can see the reactions like that. Yeah. Another example is double bond of the phenyl compound, which also bifunctional. It will be activated by this free radical. I think in the next Friday class I will give some supplement on some terms and maybe functional groups, okay, to help our lecture. Okay. If the monomers are polyfunctional, it's having more than 3 or more bonding sites. For example, it's glycerol. A branch macromolecules can be produced, and when they have this, we can make a 3D networks. Okay, 3D networks, which means that the branch and crosslink, they will create a 3D, like a 3D chains. Okay, 3D chains. Okay. So actually, depending on how you perceive the polymers, it's not always the polymers that uh, we are imagine, like, oh, it has like really really long chains. Well, perhaps one way to say, okay, that's polymer, but somehow we can create our own architecture. So I think that's why the trends in polymers is always happening, because it's really useful. They can be synthesized with low energy, like in room temperature. You can synthesize, and then you can make out the polymerizations. And to make, for example, to make crosslink, maybe you're just needed the UV, or maybe some light, or maybe just increasing a small temperature. Maybe it will help the crosslink. But the important point is you can easily adjust, you can easily tune the polymers, like what property you want, what functional groups you want. It's easy to be adjusted. Okay? And another terms that is in functionality is homopolymer. If we have only one species, okay, or copolymer if we have two types of monomer unit. So maybe we want to make like AB, AB, AB. We can do that also. And three different monomers also fine. Third polymer. Okay. And we have here copolymers. We have at least four different structure. We call the statistical copolymers, alternating copolymers, block copolymers, graph copolymers. I believe it will be very easy to be observed with the picture. So A is statistics. Okay. So the statistics means the distribution will be random. It's a random distribution. So statistic or statistical copolymers. Alternating copolymers, it alternates. So A, B, A, B, A, B is alternate. And then block copolymers, it makes in one side A and one side B. And usually this block or graph fit is also commercially available for experimental use, because it's easy to be adjusted. So we can polymerize something from this block or graph. And for grafting, it's like the primary chain is maybe A, and it has branches, which is B. We call it grafting. So I think if you just know from this picture, I think the worst is just explanation. So whenever you are going to explain the difference between the statistical copolymers, the alternating block and graph, I think you can easily draw and then explain. What time do we have? It should be until 6:20. I think I will just stop until here. Okay, if this is okay. And I will continue Friday. But before continuing this, I will add some supplement, a little bit organic chemistry terms, just to review and familiarize with the basic chemistry we have. Okay. So I think that is for today.